That's one of the graduation party. Yeah. Easily. Probably just because you invited everyone, but still. There you go. I know.
Okay, so for Part D, it's saying tickets were sold at this rate. And we know when we integrate a rate, we end up with whatever's in the numerator of that unit. So tickets per hour is a rate, we integrate it, we end up with tickets. Right, because integrating over time is the same as multiplying times time, basically. Okay. So the tricky thing is that, and you don't have to come up with a graph, I just put the graph there just to show you graphically what's happening. If you graphed that function, it would look like that. Notice that they're not asking you to show how many tickets sold over the entire 9-hour interval. They're asking you to only do the 3-hour interval. Okay, so after you do your FNs on your calculator, what do you have?
Cheese.
Only in Wisconsin.
I got the Snapchat that you sent me and I laughed really hard. I reached out, I really genuinely grabbed his shirt. It tore all the way down. My shirt is so big. All these friends were there, they were like,
Gotcha. Okay, makes sense. All right, so what did you get?
it told me I have an error.
Okay, put brackets around the tower. Oh no, you don't have to do it. 550 times x. Is this a minus sign or is that an opposite sign?
Oh, I'll have a minus sign.
Okay, that's probably why, yeah. Yeah, the opposite. Yeah, the opposite sign is, see how it's a little shorter too, yeah. Does anybody have an answer yet? This is definitely graphic calculator.
I know.
Now, if you notice my notes above there, my notes above there basically say that in these instructions, and these are really typical instructions in Part D, they're expecting you to set up the integral and then find the answer with fint. Okay, that's really what they're expecting you to do. That they purposely give you a function that you don't know how to integrate. They don't want you to spend a lot of time integrating it. Okay, not with a calculator in your hand. Does anybody have an expression for the integral they want to share? We discussed yesterday about the importance of setting up an integral appropriately. So what do you need for the proper setup here? What do we need for the proper setup for the integral? Give me something. Tom, what do you have? Okay, Tom says you need one of these things, right? The integration sign. What else do you need?
Equation
Okay, what is the equation?
5/5 dt e to the negative t over 2.
Yep. And t or x. In fact, you know, I agree with what Tom is saying here. Let's get that t, since it's written in terms of t. What else do we need?
dt.
We need a dt. What else do we need? And what are they? 0 to 3, okay? And I'll show you, underneath the purple bar is the actual rubric that the graders use to grade this problem. So we'll show you how the point distribution kind of works. Okay, so we throw that in our fint, and we get an answer. And what answer do we get? 973. Is that what everyone's getting? Okay. Did you get any decimals? It was exactly 973?
No, but it had to be the 2 years.
Okay, good. Yeah. And they're going to give you an approximate. Did we get like 972 point something? Okay, so the idea then is we need to have enough knowledge about this problem to know that we need to round to the nearest integer. We need to be able to articulate that we are representing that number represents the ticket sold. Okay, so those are the two big things in the answer. So if you look at that, if you look at their answer here, this is a 2-point question. You get 1 point for setting up the integrand, so that's 1 point right here. And then you get 1 point for articulating the answer here. Okay? And it looks like they put the limits in with the answer points. Sometimes they do funny stuff like that. Okay? So, you know, with these type of accumulation problems, with these type of problems that have this physical representation, we have to be able to articulate that we know we're selling tickets, and we know we can't sell a fraction of a ticket. So if somebody said 972, my guess is that they probably also would have gotten both points because they're approximately between 972 and 973 tickets sold. Okay? So each day now we're going to start incorporating these rubrics just to kind of show you how they're grading the setup and your answer with physical significance. So if we kind of look at the rubric here for today, we're going to continue to talk about finding area. Okay, so we're going to continue to talk about this integration process, but we're going to have more than one graph now, more than one function on the graph. And so we're going to actually be trapping area between two functions. Okay. So we're going to start out with this basic scenario, which I could have had you do last chapter. Find the area between the secant squared curve and the x-axis, which, if you think about the x-axis, it's a horizontal line, which means it's a function. And that function looks like y equals 0. Okay? So if I asked you this last chapter, you might have just said, well, the area equals integrating what function? Secant squared of x dx between the what limits? 0 and pi over 4, okay? In reality, We're doing that. Okay, we're really trapping it between that secant curve and the x-axis. Okay, mathematically those are the same. We should be able to integrate this without a calculator. This is one that we need to know. How many know this on? How many know this antiderivative of secant squared off the top of their head? Okay, a few people. That's okay. How many think they might have a gut feeling as to what it is? A few more? Anybody want to take a chance and share their gut feeling? Tangent, right? Secant and tangent always seem to go together. Okay, secant squared, the derivative of tangent is secant squared, so the integral of secant squared must be tangent, right? Working backwards. Okay. The antiderivative is tangent, is when we split it sine over cosine, and we ended up getting that opposite natural log of cosine. Yeah. So, but this is one that's really common. If we have tan x and we take the derivative, we end up with secant squared x. Okay? If we take the antiderivative, then we start with secant squared, we end up with tangent. Okay? So a really common one. So we know when we take the antiderivative here, we get tangent. And we have to evaluate that from 0 to pi over 4. Okay? What's the antiderivative of 0?
0.
How do you know the antiderivative of 0 is 0?
What else would it be?
Yeah, what else would it be? Right, here's y equals 0. How much area is beneath that or trapped between this and the y-axis?
Nothing.
Nothing, right? It is the y-axis. So the antiderivative of this function 0, y equals 0, must be 0, because there's no area trapped between it and the axis. Okay? Okay, how many know for sure what the tangent of pi over 4 is? These are some really common ones. These are like must-knows. Okay, we got a few for sure's. How many think they might have a gut feeling? A few more? What's our gut feeling? 1, right? Tangent, pi over 4 is that 45-degree line, right? Okay, and think about tangent. Tangent is nothing more than slope. What's the slope of that line? 45 degrees. It goes up and over the same amount?
1.
1, exactly. So tangent of pi over 4 must be 1. Anybody know what tangent of 0 is? 0. Yeah, if it's asking you to evaluate it, it better not be undefined, I hope. Okay? So what is the area between those two curves? 1, exactly. So the area here equals 1. Units squared. We don't have any units here, but we know area is square units. So we could actually always tack on a unit squared. Always impresses graders. Okay. So as long as we have a function that's above another function over an interval, we should be able to look at those two functions and find the area that's trapped in between. Okay? So what I want you to do is take a moment at your table and come up with a method to find the area trapped between those two functions. Okay, we already talked about just this function already all going all the way down to the axis. But what if we have another function coming across that same interval from 0 to pi over 4? Does it make sense to? I just want the area trapped here. So do I want everything down to the axis?
No.
Because I don't want to go all the way down. I only want to go down to the sine curve. So go ahead and come up with an expression So a correct integration expression, okay? And then now that you know the antiderivative of secant squared, we should be able to do this without a calculator. Yeah, so at your table, why don't you go ahead and figure that one out. Over 2, yeah, square root of 2 over 2, exactly. Awesome. Okay, so because whenever we talk about area under curve, we're talking about that space that's tracking the curve in the x-axis. Oh, gotcha. Okay, so just peeking around, I'm just writing down what people have here, which is looking really good. And so my question is, and that looks really good. You know, this is what people have written down. Can we write that with one integral sign?
Yeah.
What allows us to do that? Exactly, the same bounds on the upper and lower bounds on the integration symbol would allow us to write that as 1 if we wanted to. Typically, that's how we see it. Is we write it as 1, but this is certainly okay. Looks good. Okay, and now I'm just kind of seeing that people have antiderivatives here. What's the antiderivative of sine? We know, I'll put the values of tangent. Okay. Does anybody know the value of the cosine of pi over 4? Square root of 2 over 2. So there's our pi over 4 values. We're going to have to subtract our 0 values. What's tangent of 0? 0. Cosine of 0? 1, exactly. Okay. So how much is the value of the area trapped between these two curves?
0.707, or square root of 2.
Square root of 2 over 2. Units squared. Okay. Does that answer right there? Why did I switch the? I evaluated the tangent plus cosine at pi over 4. These are my upper bounds, right? We always take our upper bounds minus our lower bounds. So there's my values at the upper bounds minus my values at the lower bounds. Okay. Does that make sense? Okay. So what happens then if we just flip that sine curve? Okay? Bigger area, right? We know we're going to end up with a bigger answer. Okay? Tom.
And then you subtract them still because the sign is already negative.
Exact. Okay, so Thomas catching on is that we have a negative function here. So when you say adding the areas, we'd have to make sure these areas were both positive, right? And then we can add them. Or what's the same as adding a positive? Subtracting a negative. Okay? So since the function is now negative, we're going to still subtract these two, but we're subtracting a negative function that's going to give us a positive value. So the idea is that we've got the single method now. We subtracted the functions on the top, and we subtracted the functions on the bottom. It's just that one of them was negative. So subtracting that negative function is the same as adding a positive. So we can still just subtract these functions. I'll go through that again. I know we kind of went through that a little quick, but we have secant squared x, and we're still going to subtract the bottom function. In other words, we're taking the big function and we're subtracting the little function. But the little function is what? Negative sine x. So we're taking this upper function and we're subtracting the lower function, which is negative. And what is subtracting a negative? That's the same as adding. Didn't you say you wanted to add this area and this area? Yeah. And, yeah. Isn't this adding? Yeah, it is.
A lot of work in between.
Okay, it's just adding. Thanks. But the idea is that if we always subtract the little from the big, or in other words, we always go top minus bottom, if we subtract that, if we always subtract, we'll always get the right answer. Because when we have functions that are beneath the horizontal axis, subtracting a negative function is the same as adding. Okay. I put that on your review yesterday. I'll also email attendance. Sorry about that. Okay. So going through this, we know this is tan x. We know this is going to end up being a plus. What's the antiderivative of sine x? Negative cosine. Zero to pi over 4. So we have tan pi over 4 plus a negative cosine pi over 4 minus tan 0 plus a negative cosine 0. Oops, that's supposed to be a 0. So we have 1 plus a negative root 2 over 2. And we have 0 plus a negative 1. So how much do we have now? Yeah, we've got 2 right minus negative, so we have 2 minus square root of 2 over 2. And that's about as simple as you can get. Nope. Nope. Yeah, you've earned the right not to combine fractions. We're not in algebra anymore. In fact, I've seen people leave it like that and still be okay. Put unit squared on there. Okay. So subtracting a negative function is the same as, like you said, you wanted to add those two regions. I've also seen people say, well, let's take this region. I know it's positive. Let's just make this region positive by doing an absolute value. Remember that yesterday? Get the same answer. Totally fine. Okay. Subtracting a negative, same as adding. Okay. So the idea then is no matter where those functions are, all we really have to do is make sure we're subtracting the little one from the big one. So the bigger function is the one that's higher up. It's got bigger y values. The little function is farther down. It's got littler y values. And we're just going to subtract those two. Is that okay? Okay. Sometimes, you know, that first one we just started at 0 and ended at pi over 4, and the functions didn't even intersect. Right? We had these two regions, and they didn't even touch each other at all. Sometimes we have, and most of the time, we have something like this, where we have an upper function and a lower function, and they intersect. And we want to find the area of the region. Okay, in other words, the enclosed space. So in this situation, what do we have to figure out? Well, okay, we do have to figure out the area. I agree. But what do we need to know in order to set up the integral? Where they intersect. How are we going to figure out where they intersect?
Look at the graph.
Okay, can we just see that on the graph? Yeah. Do you know what those points are?
0, 2, 1.
Yep, I agree. -2, -2. Yeah, I agree. And 1, 1. What if we didn't have a graph? And what if we didn't really want to graph it? How would we find those points? Going back to algebra 2. What do we do? To find the points of intersection. What do we have to do? Okay, what do you mean you saw the system? That's a fancy way of saying you could. In not such fancy terms, you do what with the two functions? Not necessarily add them together. Set them equal to each other, right? We want to know where their values are equal. So we want to know where 2 minus x squared equals x. Okay? So if I take everything over to the right-hand side, that makes my x squared term positive, which is much easier for factoring. Then we have x squared plus x minus 2 equals 0. And when we have quadratics, the first thing hopefully we think about when solving these things is we have to do what with this? Yep, we have to factor. And that factors into what? Yep. Yeah, I think. Okay, no worries. All right, we need a plus 1x. So my solution to that quadratic then is x equal to 1, right? That's that point. and x equal to -2, right? When we set those equal to 0. And that gets us our points. And where do those values show up then? Oh, good catch. Where do those values show up then in the calculus expression? Upper bound and lower bound, exactly. We're going to start accumulating area here, and we're going to stop accumulating area here. So as we move from here to here, we're going to trap ourselves between these two functions, and we're going to fill in that space. In fact, we could almost look at this as, a lot of times they'll do this, right? They'll start filling in this space with rectangles. We could almost do a Riemann sum. We could just fill these rectangles in from left to right. So go ahead, come up with the expression for me to grade on the integral. What does that look like? What do we have? So we know that as long as we take our big function and subtract our little function, we're good to go. Okay? Notice the little function and the big function sometimes are negative and sometimes are positive. But is the big function always bigger than the little function across the whole interval? Which one is the big function? Yeah, the top one, which is the red function. Bless you. Is that red function always bigger than the green function in that interval? Yes. Yeah. Do we care what happens outside the interval? No. We don't. Exactly. Outside the interval, those responsibilities switch. That's a basis of tomorrow's discussion.
So would you make the x negative?
Nope.
So you can just subtract it?
Just subtract it. Okay. So we're going to have our lower bound at -2 and our upper bound at 1. And what's our big function? 2 minus x squared. What's our little function? X. So we are going to subtract our smaller function. Okay, this is where it gets really picky. We're subtracting two functions, and College Board really likes to see the function in brackets and the other function in brackets, so they can see big minus little. They really like that. Okay? And then they want to see the whole thing in brackets because you're integrating the whole thing. Does that make sense? And then your dx. That would be the proper setup. Okay? That's that 2 or 3, occasionally 4 point process. Okay? They actually will mark off if you don't have the correct brackets. Now I made square brackets on the outside. If you didn't do square brackets, that would be okay. Okay? But they want to see the complete set of brackets. Right? Yes, you could. Ryan's saying, can I just do the red minus the green and make them separate integrals? Absolutely. Okay. So there's our setup. And then we can go ahead and integrate this. So this one, it's pretty reasonable that you would see this on no calculator part of the test. Definitely. Okay. So when we integrate 2, we get what?
0.
I disagree. When we take a derivative of 2, we get 0.
Oh.
2x. When we integrate x squared, we get x cubed over 3. Exactly, it's the same thing. When we integrate x, we get x squared over 2. And we're gonna evaluate that at 1 and then evaluate that at -2. Okay? So I'm gonna go ahead and substitute 1 in there. 2 times 1 minus 1 cubed over 3 minus 1 squared over 2. There's my upper bound. And then I'm gonna put my lower bound in there. And we're gonna have enough negatives in here to drive us a little crazy. We have that. Okay, so this first one, 2 minus 1/3 minus 1/2, that's not that bad. -4, is this ended up being a plus or a minus right here? This ends up being a plus. Yep, 8/3. Does this end up being a plus or a minus here?
Minus.
This ends up being a minus, just a 2, right?
Yep.
Okay. So that ends up being a -6 plus 8/3. Oops. Actually put these in brackets, although we don't really have to. Okay. And now we got a bunch of fractions to deal with. Yay. Love fractions. Pardon me? Right there?
Yeah.
Great. Okay. So I'm looking at this and I see a common denominator of 6. So that's 2/6. That's 3/6. Wow, I should reverse those. Uh-huh. Is that all okay? Okay, awesome. And then I have a 12/6. So what's 12 minus 2? 10 minus 3. So we know this whole thing is 7/6. This is a, I'm going to put a 6 again. 16/6. Ooh, what's this one? 36/6. So it's a -36 plus 16. -20/6. So we end up with an area of how much? 27/6. That's about as difficult of fractions as I'll have to deal with. Yes, definitely. Okay. Is it okay so far? All right, so just to try, let me just take a look at this. Yeah, just to try a couple of AP level questions here. Okay, there we go. This first one is a calculator. Notice the instructions at the top say you can use a graphing calculator. We're just doing A and B. Okay. So go ahead at your tables and come up with the answer for the area with your calculator. So it should be a quick process. Okay. And then B is going to require a little thinking. And what I did is I gave you the scoring rubric ahead of time here. So I need the correct limits and the correct integrand and the correct answer with units to get all three of those points.
Good question.
We have a sine and an x cubed. So which one looks like a sine function? From 0 to pi. That's from 0 to 2.
In this pattern.
2 pi. Which one's on top? Just subtract.
What's the area?
We're talking about positive, right? I mean, we're talking about area, right? And so if you think about looking at this function, a lot of it is below the axis. That's true. So when we subtract that bottom function, we're subtracting a negative, which is the same as adding a positive. So we'll end up with that same phenomenon.
We subtract that.
And subtract that. And subtract the little one. No. Oh, right. Yes, you could. Oh, totally. Does everyone understand our conversation that's going on here?
So can you just do 0 to 2 of x cubed minus 4x?
Absolutely. Okay, so we've got this table over here saying I am just going to go from 0 to 2, and this is my cubic. So I'm going to take this minus my cubic, because my cubic is beneath the axis, and I'm just going to integrate this from 0 to 4, because this bump will fit right in here. Totally fine. Okay? So we're seeing two possible scenarios. We can go from 0 to 2, and we can take a sine pi x minus x cubed minus 4x in brackets.
I mean, we got the tell you.
There would be one proper setup. Or 0 to 2 of 0 minus x cubed minus 4x dx. Okay? Now, why, in that second one, that's taking the bump and putting it into the hole. Okay? Why did I have to put 0 minus? Why did I have to put 0 minus in that second expression? That's the right answer.
Yeah, subtract the lower.
Yeah, because remember, we're trapping stuff between the axis and the function. The axis is now the bigger function, and the cubic is now the little function. Okay? Did anybody come up with an answer? For that? For B, or for A, find the area? Or, yes, the answer should be 4. Right? Let's talk about this this letter B here. We have a horizontal line that splits the region in R into two equal parts. Right, but do not evaluate the integral expression for the area of part R that is below this line. How do we find this area? This goes back to a bounded area. We need to find those 2 points. How do we find those 2 points? Yep, so we have to set our x cubed minus 4x equal to 2. Okay? You're absolutely right. Good catch. Equal to negative 2. Okay, now, does that factor easily? Say no. No. Good. It's a cubic, right? I'm not going to try to factor a cubic. So we're going to go into our calculator and we're going to do an intersect. And we're going to find those bounds. And we're gonna round those to 3 decimal places. Okay? So go ahead and set up a calc intersect and get those decimal places.
How do you do a calculus? Oh, wait,
You have to be in the graph mode. For doing the intersect, put them in your y1 and y2 first. So you put these in y1 and y2, so that we can see it on the graph. Go into, you see your button that says draw. It's the program button. So it's a blue draw, and then option 1 is clear drawing. Yeah, if there's something on your screen that you don't want from a Riemann sum or a slope field program, it's because you have a drawing on your screen. Let me know. How do you get rid of that? You go to your draw key, which is your program key, so second to draw, and then clear drawing. There you go. Okay, so now we can do a second. Intersect. And then we're gonna have to click, we're gonna have to go here to that first intersect over here. And then hit enter for your cursor, enter. Yeah, it'll automatically jump to the okay, so we are at 1.539. So this first intersect is 0.539. Comma -2. That's that first point. What's the second point? Yeah, right. Or right. Right side. Okay. Okay, so y equals, you see how this does not have a black block? Do that, and then this automatically turns it off. Okay, one program. And go on. No, you don't have to leave that.
Still could be.
Okay, so we've got some sort of thing that's turned down.
1.675.
Okay.
It's been showing up. I've gotten it to work, but I was like,
There must be some setting in there. Does anybody have the other intersection? Did we find this point over here? 1.675? Thank you. 1.675 comma -2. Okay. So what does this integral look like? My lower bound is what? What's my lower bound? .539. What's my upper bound? 1.675. What are my two functions? What's my big function in this region? What's my big function? No, what's the function that's higher up? -2 is bigger, right? -2 is on the top and the cubic is on the bottom. -2 is less negative. Does that make sense? Okay, and then we have to subtract the cubic. X cubed minus 4x dx. Okay. So on this problem, they are just grading the setup. You know how it says, write but do not solve the integral. Okay, they just want you to set it up. Done. Okay. Questions about that? The last page we're not going to do. It's a really similar problem. I just wanted to see how much time we had left. Okay. So we've got 7-2 day 1.
That
Oh,
password on it.
yeah, the password is Oscar, as in the Grouch. I'll take that passcode off. It expires automatically too.